This lesson is for FST Lesson 9.1 on nth roots. Students will need both a baby calculator and a graphing calculator for this lesson. Root functions, when graphed, will look like this little graph here. It almost looks like a parabola, but on the side, and also one half of the parabola has been eliminated. The reason for that is when you write a root problem in rational form, meaning in fraction form, we're only going to allow x's to be positive, and we'll talk more about that both in this lesson and in the next. You can also write root functions in rational form, which means you're using this symbol. Know that the root here and the bottom of the fraction here need to match in order for those to be considered root functions. On the radical form of a root problem, know that you could be working with either positives or negatives. Usually the negatives, there's only an answer when the root is odd. So if x is, or your base, is a negative number and the root is even, then there's no real answer that you can come up with. We know that if we look at this first one here, the base, or the x here, is a negative number. This is indeed a square root number, which means the root is even. There is no real answer, but we are able to find a complex or imaginary answer because we can break it up into -1 and 81. The square root of 81 is positive and -9. Square root of -1 we know to be an I, so we'd get an answer there that is complex or imaginary. That means there's no real answer, even though we could get a complex answer. We are able to handle radical problems that have a negative base, but only when the root is odd, because an odd number of negatives multiplied together will still result in a negative. So here we know that the answer is going to be -2. Many of these questions students will have to handle without the use of a calculator. You will be allowed to use a baby calculator in those situations. So if you're raising to the 1/3 power, that is identical to taking the cube root of the base. So you're trying to find a number times itself 3 times that equals 125, and each of those numbers needs to be identical to each other. So you'll have to do trial and error there. Typically, if it ends in a 5 or a 0, 5 would be a good option to try. 5 times 5 times 5 is indeed 125, so 5 is my result. If you're working with a fraction and you're raising to a fraction answer, a reminder here that raising to the 1/2 is the same as taking the square root. So we're doing the square root of 1 and the square root of 36. Square root of 1 is 1, square root of 36 is 6, so our final answer there is 1/6. It is important for students to pay attention to the presence of parentheses and how those relate to negative numbers. If the base is negative and it's wrapped in parentheses, then this problem would have no solution, because there's no way to get 4 things multiplied together that can equal a negative. However, the question next to it is able to be performed. Because of the order of operations here, the negative is not necessarily attached to the base of 16. We could do the power function or the root function first and then take the opposite of the answer, because technically, with the order of operations, the power would take priority over taking the opposite of something. So we could do the 4th root of 16, which is 2, and then we could take the opposite of the answer. So students need to pay attention to whether or not there are parentheses and where those parentheses place a negative. Going along with that same idea, let's take a look at these 5 problems. Some of the things that you'll have to do in the lesson are simply to figure out if there is an answer or not. If you take the 4th root of a number, we could type that in on the calculator and we'd get a real answer. Typically it would be a decimal answer. Students wouldn't be forced to use a baby calculator to figure this one out. You would be allowed to use a graphing or scientific to actually calculate what the 4th root of 33 would be. If you're forced to use a baby calculator on a question like this, it would be a number that you could easily figure out, like a whole number. Question B, you would also be able to get a real answer here because those 2 questions are indeed identical. A is in radical form and B is in rational form. Now let's look at what happens when we incorporate a negative. If you look at C versus D, one has parentheses and one doesn't. C we would be able to figure out, so there would be a real solution here, but on D there wouldn't, because there's no way for us to figure out a number times itself 4 times that equals -33. So C has an answer, but D does not. And now let's figure out which one E matches with. This negative 33 is underneath this radical bar, and that radical bar behaves like a grouping symbol. So there are indeed imaginary parentheses around that negative number. So E and D are actually the same question. Both of them will have no solution. So let's talk a little bit further about how many solutions you should be able to expect. When you're working with real roots, every positive number is either going to have 2 or 1 root, depending upon if the root you're doing is even or odd. Every negative number is either going to have no solution or 1 solution, again, depending upon whether or not it's even or odd. Remember that when it's positive, you can do a root either in radical form or rational form. However, when the x is a negative, you have to pay attention to what type of root it is. It needs to be odd, and you can only do it in radical form. Let's use this same information now in picture form or on a graph. This information is taken out of your textbook, page 563. I would recommend taking a moment to read through that page, as the book does a fairly decent job of explaining why the answers are the way that they are. What I like about this is now this is a picture version of everything we just looked at in the yellow boxes. If you're raising to an odd power, hopefully students remember the shape of that graph. It's kind of that squiggly snake shape. And when you are trying to find a negative result will intersect that graph 1 time, so there's 1 solution. If you're trying to find an answer that's positive, a positive answer will intersect the graph once, so there will be 1 solution in either case. So let's illustrate how this picture relates to the yellow box. Whether you have a positive or a negative, if the root you're dealing with is odd, you're only ever going to get 1 solution, no matter what. Now let's look at the evens. If you're working with an even power, your graph will be parabolic in shape. And if you're trying to find where it intersects with a positive number, it's pretty clear here that it's going to intersect twice, meaning there will be 2 answers. However, when you try to work with a negative number will never intersect when it's even. So in those situations, positive or negative numbers are either going to have 2 answers when it's even or no answers when it's even. So it's the same information we had back here, only here it's in words, and here it's in picture form. Again, there's some more information in the book given that I'd recommend that you take a moment to read through. The last thing we're going to cover in the video today is how to solve with roots. Keep in mind that you could use a radical or a rational to finish these. I'm going to show you 2 different types of solving. This first one we're going to solve for r, and we're going to basically rearrange all the different parts of the formula. The r is being cubed and multiplied by pi and multiplied by 4/3. If we want the r to stay, everything else needs to move to the other side. The way that you do that is by picking up the thing that's furthest away from r and moving that to the other side using algebra. Currently the 4/3 is the furthest away from the r. It's being multiplied, so I'm going to multiply by its reciprocal. If you had said that you want to divide there, you wouldn't be wrong, but know that typically the way we get rid of fractions is by multiplying by the reciprocal. When you rewrite on the left, you can either put the v on the top or on the side of the fraction, but please don't put a v on the top and the bottom. Now, we still have a pi sitting there. Know that you could also maneuver the pi with the fraction. To get rid of the pi that's currently being multiplied, we should divide on both sides by pi. So I can move that with the 4 because the 4 is already on the denominator. So I'm just going to go ahead and combine those 2 steps. Know that you are allowed to do that if you've got multiple multiplications going on. To get rid of the cubic here, or raising to the 3, I've got the option of taking the cube root of both sides, or we can raise to the 1/3 power on both sides. If you decide to raise to the 1/3 power, just make sure that you put it with everything, or just put your entire problem in parentheses. So you've got 2 answers there. You can say cube root, or you can write it as 3/4 pi v, put it all in parentheses and raise it to the 1/3 power. Now I want to contrast this question to this one over here. This one over here we're going to solve for g, but we're going to be able to come up with a final numerical answer rather than a rearrangement of what we see. The thing that's furthest away from the g is the 0.5 here. Multiplying by a half is the same as, or trying to get rid of multiplying by 1/2, we should multiply by 2 because that's the reciprocal of a half. So I'm going to multiply both sides by 2 here. That's going to cancel out the half and the 2 on that side. On the left-hand side, I'm going to get a 6. And I still need to get rid of raising to the 50th power. You are allowed to do a 50th root here, but I think it's going to be easier for you just to simply raise to the 1/50 power. We're not multiplying by 1/50, we're raising to the 1/50 power. You would type that in on your calculator, and you'd get about 1.04 there approximately for g, depending upon what you round to.